Yes, today we are going to learn about solution of first order linear PDEs by method of characteristics. And the word PDEs stands for partial differential equations. So we are learning about the solution of first order linear PDEs by method of characteristics. Then we are going to begin by looking at a general case of a first order linear PDE. And a general case of first order linear PDE is usually given by A, the partial of u with respect to x, plus B, the partial of u with respect to y, plus Cu is equals to f of x, y, and u, where A, B, C, and F are continuous functions of x and y, and A and B should not be equal to 0. A and B should not be equal to 0. So we are going to look at an example. We are going to look at an example on how to solve a first order linear PDE by method of characteristics. Okay, so this is our first example. Now, when you are solving first order linear PDE by method of characteristics, we begin by identifying the coefficients of the partial of u with respect to x and the coefficient of the partial of u with respect to y. And therefore, we begin by writing our characteristic. Equation. So I want us to solve together. Solution. Okay, so we're going to begin by writing the characteristic equation. We're going to begin by writing our characteristic equation, and the characteristic equation in this case will be given by dy over dx is equals to, now we are going to begin with the coefficient of the partial of u with respect to y, then it will be our b. Then the coefficient of the partial of u with respect to x is a. And then the next thing, now we cross multiply. We are going to cross multiply. So we are going to have a multiplied by dy. I'm going to have a multiplied by dy. So I'm going to have a dy is equals to b dx. We have a dy is equals to b dx. Then when we take this one to the other side, we will have n dy minus b dx is equals to 0. Then we can put our equal signs there like that. Then from there we can integrate this one. We can integrate the whole of this one. Integrating the whole of this one like that. Once we integrate the whole of that one like that, we are going to have ay minus bx, because when we integrate a with respect to y, we get ay. When we integrate b with respect to x, we get bx. So it is going to be ay minus bx. Then we can let this one to be equal to a given constant. Let's call it c for a constant. Then after obtaining our constant, we now go next to the characteristic curves. So I'm going to write the characteristic curves. We now go next to the characteristic curves. Then we obtain the characteristic curves from our previous constant that we obtained from our characteristic equation. And so now in a characteristic curves, we are going to introduce new variables. We are going to introduce new variables, and we shall be using this variable. We shall be calling it xi. Then we shall also be using this other variable that we shall be calling it nu. So this one shall be our xi, and this one shall be our nu, the two new variables. Now, in our characteristic curves, we go to our previous characteristic constants. Then we let the constants, if it is 1, we will let one of these variables to take it. Then if we add two, supposing we add two constants, then we would have let one constant to be equal to our xi and another constant to be equal to our nu. But because we have one constant, we can let this, our first constant, to be equal to our first variable, or maybe our second one, nu. So for my case, I will let the first constant to be equal to nu. So I will let the first constant to be equal to nu. So nu is equal to ay minus bx. Ay minus b ay minus bx. Then now, remember we should also have another function. We should also have another function for xi. But for us to come up with our function xi, we are going to first of all differentiate this function for nu, with respect to both x and y. So if we differentiate our nu with respect to x partially, our nu x will be equal to, of course we consider the term that has x. So our nu x will be equal to negative b. Then we also obtain our nu y. Our nu y simply means we are going to differentiate this function with respect to y partially. Therefore, once we differentiate this function with respect to y partially, we are going to have a. Then now with these values of nu x and nu y, we can be able to let our xi to be either x or y, or maybe ay plus bx, or any other function, so long as Jacobian rule will be obeyed. So in this case, I will let my xi to be equal to x. Then if this is my xi, or the function of my xi, the same way I have done here, I will also do here. So I will obtain xix, which will be equal to what? I will obtain xix. So I will differentiate this function with respect to x partially. This will be equal to 1. Then I will also obtain xiy. And once I differentiate xi with respect to y partially, I will get 0. Then if we test Jacobian rule, that is of xi nu, we should not get 0. So if we test Jacobian rule of xi nu, we should not get 0. And this is how we test Jacobian rule. We take the value of xix times the value of nu y minus the value of xiy times the value of nu x. So this is how we test it. So we're going to get xix times nu y minus xiy times nu x. This should not be equal to 0. So in this case I have 1. In this case I have 1 times a. This will be a minus negative b times 0 minus negative b times 0. This is equals to a, and therefore Jacobian rule is obeyed. Then, since Jacobian rule is obeyed, we are going to obtain the values of the partial of u with respect to x, and also obtain the partial of u with respect to y in terms of the new variables. That is xi and nu. So now we are going to begin by obtaining the partial of u with respect to x. For us to obtain the partial of u with respect to x, we are going to differentiate u with respect to x, but in terms of both xi and nu. So I will have the partial of u with respect to xi. I will multiply by the partial of xi with respect to x. Then I will also add the partial of u with respect to nu multiplied by the partial of nu with respect to x. Then this can also be written in the form the partial of u with respect to x to be equal to the partial of u with respect to xi dot, we can call this one to be xix, plus the partial of u with respect to nu dot, we can call this one to be nu x, like that. Then, because we had obtained the values of xix, the values of xiy, nu x and nu y, we are going to substitute here. Here we need to substitute the value of xix and the value of nu x, so that now our partial of u with respect to x, will be equal to, when I substitute the value of xix, it is just 1, so I will just multiply by 1, and therefore I will have the partial of u with respect to xi. Then plus the value of nu x is negative b, so I will substitute negative b where there is nu x. So it is going to be equal to negative b. It will be like this, negative b, then the partial of u with respect to nu, like that. So that is the value of the partial of u with respect to x. So this is the value of u, the value of the partial of u with respect to x in terms of xi and nu. So we are going to obtain again the value of u with respect to y, but in terms of xi and nu. So this will be equal to the partial of u with respect to xi. Then instead of multiplying with the partial of xi with respect to y, I will just write my xi y. Then plus the partial of u with respect to nu. Instead of writing the partial of nu with respect to y, I will just write nu y. This one is simply to mean the partial of nu with respect to y, and also here this will simply means the partial of xi with respect to y. Then remember that we had obtained the values of xiy and the values of nu y. We had obtained the values of xiy and the value of nu y. So now we are going to substitute them. Therefore, the partial of u with respect to y will be equal to xiy. We obtained xiy as 0. And therefore, we are going to substitute 0 here. 0 multiplied by this, we are going to get 0. So this will be 0 plus. We had obtained the value of nu y. And the value of nu y, we got it as a. So we are going to substitute our a here. So a times this one will be a, the partial of u with respect to nu. So this one can simply finally be equal to the partial of u with respect to y. This will be equal to a partial u with respect to nu. So this is the value of the partial of u with respect to y in terms of xi and nu. Then remember that our function was in the form, our function was this one, a partial u with respect to x plus b partial u with respect to y plus cu is equals to 0. That was our function. And we have obtained the value of the partial of u with respect to x. We have also obtained the value of the partial of u with respect to y. So now we are going to substitute them here. We are going to substitute them there. Okay. So now we are going to substitute them like this. We are going to have a into brackets the partial of u with respect to x. And remember, we obtained the partial of u with respect to x as partial u with respect to xi minus b partial u with respect to no. So that is the value that we are going to substitute here. So this will be equal to, this will be the partial of u with respect to xi minus b the partial of u with respect to no. That is the value of the partial of, that's the value of the partial of u with respect to x. Then plus b into brackets, we substitute the value of the partial of u with respect to y, and it is here. We obtain the value, the partial of u with respect to y as a partial u with respect to no. So we substitute it here. It will be a partial u with respect to no. Then we close brackets like this. Okay. Then plus cu is equals to 0. Plus cu is equals to 0. Then now we are going to open the brackets. We will open the brackets. So this will be a partial u with respect to this will be a partial u with respect to xi minus a times b will be ab, then partial u with respect to no. Like that. We continue opening brackets. A times b will be plus ab partial u with respect to no. Then of course plus cu is equals to 0. Okay. Some terms will cancel here. Negative mb partial u with respect to no, positive mb partial u with respect to no. Those two terms will cancel. So they will cancel like that. Then we are going to remain with a. We are going to remain with a partial u with respect to. We are going to remain with a partial u with respect to xi plus cu. Plus cu is equals to 0. So we are going to remain with a partial u with respect to xi plus cu is equals to 0. From there, we are going to divide. We are going to divide both sides by a. I'm going to divide both sides by a so that the coefficient of the partial of u with respect to xi is 1. So we divide here by a, we divide here by a, we divide here by a. Like that. So this will be equal to, this will be finally equal to the partial of u with respect to xi plus c over a plus c over a plus c over a u is equals to 0. Of course, n divided by 0 will mean 0 divided by a will be 0. So this is called canonical form. Of the PDE. This is called the canonical form of the PDE. This is called the canonical form of the PDE. And now we are going to obtain, remember u is our dependent variable and xi is our independent variable. So we are going to obtain the value of u by integration. we are going to obtain the value of u by integration. And this is going to apply the method of integrating factor. We are going to employ the method of integrating factor. And we said that integrating factor is usually given by exponential the integral of p with respect to it depends with the independent variable of the function. So this will be p with respect to xi, because my independent variable here is xi. So in my case here, this will be equal to exponential the integral of the value of p is the coefficient of u. The coefficient of u is the value of p. Therefore, instead of p, we are going to put c over a, then with respect to xi. So this will simplify to, once we integrate c over a with respect to xi, we are going to get c over a xi. So this will be exponential c over a xi. So this will be the integrating vector, exponential c over a xi. Okay, now with our integrating factor, which is equals to exponential c over a xi, we are going now to obtain our solution. Therefore, we are going to say that our solution u will therefore be given by 1 over the integrating factor times the integral of the given function, let's say g of xy at the equal sign, and g of xy at the equal sign times the integrating factor, then with respect to the independent variable given. And in our case, we are using our independent variable there is xi. Okay, now with this, our u will therefore be equal to 1 over the integrating factor, and remember our integrating factor is exponential c over a xi. So it will be 1 over exponential c over a xi multiplied by the integral of our function at the equal sign, which is g of xy. In this case is given as 0. Our function here is 0. Therefore, we are going to have 0 multiplied by the integrating factor, that is c over a xi. Then now with respect to xi. Now in this case, we can take this one to the other side. We can multiply all the room by exponential c over a xi, then the other side by exponential c over a xi, so that this one is cancelled. Okay, so if we multiply by exponential c over a xi, and we also multiply this other side by exponential c over a xi. So in this case, this one will cancel with this one, and so we will obtain u dot exponential c over a xi being equal to 0 times exponential c over a xi will be 0. Once we integrate 0 with respect to xi, we will get 0. Then it will be 0 plus a constant. Then you can let this constant to be a function of, because we are dealing with xi, and we had only two variables, xi and nu, then this one will be a function of nu. This will be a function of nu. That will be a function of nu. So this will be simplified to u dot exponential c over a xi will be equal to g into brackets nu, which is our constant. So we also need to take this one to the other side. So by division, we are going to divide the room by exponential c over a xi. Then we divide the row by exponential c over a xi. So we are going to remain with u will be equal to exponential c over a xi, and it will be negative. So instead of writing 1 over exponential c over a xi, which is here, we're going to just negate the power, so that we're going to have exponential power negative c over a xi to mean 1 over exponential c over a xi. Then g of nu. Now this is our function of u. This is our function of u in terms of xi and nu. But remember, previously we had let xi to be x and nu to be ay minus bx. So we are going to substitute the value of xi and nu in this case. Therefore, we are going to have u is equals to exponential negative c over a. Instead of xi, we are going to put x, like that. Then g of our nu is ay minus bx. So it will be ay minus bx. So this is the solution. So this is the solution of the given first order linear PDE. So I hope you liked it. Please comment, like, subscribe, and share to your friends. Thank you so much.